Good morning, everyone. This is Jim Chastain with EasyPower. Today's refresher episode is a continuation or extension of what we did last week. Last week we focused on transient motor start and writing scripts. The extension of that and the more complete stability package is referred to as dynamic stability, and that includes, in addition to motor simulation, generators. And so real briefly, both of these simulation modules are based upon power flow, and the purpose is to design and troubleshoot cases of starting motors, changing loads on generators, and going through several different scenarios and plant operations utilizing power flow, but being able to capture simulation over time, and essentially I like to think of it as power flow to the max, because you can have power flow calculations at varying discrete increments over an extended time frame and be able to simulate what your system's going to do to various stimulus or loss of loads or faults. Obviously, to use either one of these tools requires power flow. Both allow you to produce scripts very quickly and then customize plots, which includes the ability to look at different buses or system elements, even remote to that where the stimulus is applied. So that the big difference now between transient motor start and full dynamic stability is the fact that we can include generators and generation modeling, and built in the tools library are a number of standard models, and all of which can be customized for any specifics that you may have on site, and utilize the manufacturer's data sheets to build out these models. And this includes the models for PV or solar farms or wind turbines. So in the simulation model, you'll see that we can include simulation models for generators, the exciters, governors, and stabilizers. And we will kind of go through a real quick example of how to import what's standard in the library, but also show where these can be customized as required for your applications. And as always, because this is based on EasyPower, you'd expect a high level of graphical user interface compatibility and ease of use, and you'll see that ultimately equates out to very fast calculations and plotting and instant delivery of system-wide results. So without further ado, let's jump into the tools. As I go into this, there are a number of pre-recorded tutorials on our website that get into much more detail on all of these elements of both transient motor start and dynamic stability. In addition, there is a couple of modules that are installed with the tools under the samples folder, and as you go to the open folder icon at the top, the tool automatically takes you to the EasyPower installed folder 1 lines, and under 1 lines is the sample subdirectory. And last week we talked about the DS1 example, and today we're going to talk primarily about DS2 example and then kind of migrate on from there. All right, so in this particular case we have kind of a typical cogen situation where we have the utility supplying the primary part of the load, the demands of the load, and then cogen supporting as much as can be supported by the internal generator. And here we have our load set up into 3 basic feeders along with an ATS that will switch over a panel that needs to have standby power available anytime there's a plant that goes down all the way. One of the features that we've included in the modeling here is a frequency sensitive relay that, as I kind of go in and look at the settings on this ABB relay, You can see that it's set up for a frequency setting to drop at 59.5, and the purpose of this is to perform or accomplish load shedding, where we have 3 different legs. Each of these relays is set up for a different sensitivity. The first is set up at 59.5 hertz. This one's set at 59 hertz. And then the third, in addition to overcurrent, is also set to drop out at 57.5. So the purpose being, if we lose utility, how quickly can the cogen keep up with picking up the load? And just to be on the safe side, we have each of these buses drop out if the frequency stalls below a certain level. So again, this is 59.5 hertz, 59 hertz, and then 57.5. So our first simulation is going to see how well the system can survive that type of scenario. Before we go there, let's look at how we set up the data. Again, I'm in Database Editor, and I'm going to look at the cogen model, the generator model for this particular case. And you'll see that, first off, from the basic icon for a generator, we have a number of other modifications to the icon that indicate it does in fact have stability data. And these include, as we go into the basic data dialog box, under stability, we enable the generator model, exciter model, and the governor model. And we've chosen to select a generic manufacturer and a standard round rotor generator, and we've pulled in the data from the library. In this case, the data includes all the subtransient variables, including X prime, X double prime, and windage. If you have a specific data sheet on a generator, you would want to enter that data in place of the generics, or if you go in and look at a specific manufacturer, they will have a more extensive listing of each of their models, again, which may be a more valid place to start if you have a customized version of any of these standard models. Likewise, under the exciter model, we're using generic, but there are others that match certain standards from IEEE. And again, by selecting these and then pulling it in from the library, most of the parameters will have some value that then gives him the characteristics of this particular simulation. So we do the same for the governor model. Again, in this case, we're using generic for a standard gas turbine, and or we would choose whatever we're going to use for our particular application. And finally, when we talk about the stabilizer, these are a little bit more complex, and if you get into a mode where you have a customized requirement, you may want to contact tech support for additional assistance, but in this case we're just going to use standard PSS2B for our stabilizer. And so as we enter each of these models, that expands the description of our icon, but by so doing, this allows us to enter in stability. And what we show now in stability, dynamic stability, is the one-line diagram here on the left with the power flow solution already solved. And the point being is you want to start in a quiescent mode or a steady state mode so you don't have any influence from an imbalance from what our initial starting point is. So at this point we have solved power flow, and on the right will be our display of the voltage and current based upon what we're asking for. So the first thing we want to do in our simulation is fault the bus. And so as we double click on this main switchgear bus, the main coming in from utility, you can see that the tool automatically plots our voltage and current. And in this case, this is the fault current for which is being protected or stimulating the reaction to the protective devices. And in reality, this will be a more accurate representation of the short circuit current because we see over time how the different elements are engaged and consequently isolate different parts of the circuit. In the log below, we can see where different contactors are falling out based upon the fault. And again, this will follow over time the different time steps as the relays are picked up and then contactors dropped out in response to the relay. Whenever we do a double click to simulate or to initiate the fault, we have the ability to control what those reactions are by going to dynamic stability options, double click, and here if we're simulating a breaker open or close, we're going to start with a 20-second simulation and a delay time, initial delay time of 1 second. Likewise to close, if we're clicking to fault a bus, we're going to initiate a zero resistance fault on the bus, run for 6 seconds with an initial delay of 1 second, and then a fault time of 7 seconds. So again, all this is customizable, and you may want to change based upon what type of simulation you're doing. Then once we've done a simulation, before we do the next, we want to reset, and as simple as it can be in the case of the utility fault, which might be to pull this particular breaker, by default, because we're on a branch, it's going to plot the voltage, the current, and then the kilowatts and the kVA, which is not all that exciting if this is the only place we're going to be monitoring. All right, what we want to do now is simulate load shedding, and so to do that, we're going to use a script that's been written. So let's go in and look at it. So essentially, we're going to run the simulation for 1 second, and we're going to open that same breaker that we were talking about, and then run for another 10 seconds. But this time, instead of just looking at the voltage and current in this one particular leg, we're going to define some specific plots. On plot 1, we want to see the generator speed for the cogen, the voltage on the cogen. So basically what we're expecting is as the frequency starts to drop on the main bus, each of these loads will in turn drop out if the cogen doesn't pick up the frequency in time. So consequently, we're going to be plotting frequency, current angle, and bus frequency. Let's see if we other plots that we want to check out. And we're also plotting the standby generator, which we're not going to worry about for now. Okay, so we're going to again pick the load shedding example. We're going to look at plot 1, and we're going to run the simulator. And so what we're looking at here is the cogen speed, the cogen voltage, current, cogen angle, power angle, and then the bus frequency. And we can see from the legend that's here in the corner, everything runs for steady state for 1 second, and then as the utility bus voltage is dropping, we can see the frequency here at the bottom drops to 59.878, looks like at the first step, and then ultimately drops down to 59.439 before starting to recover. And as we kind of see, the net effect at the end of the time is we have lost the first leg, which dropped out at 59.5, but because the bus, or the second leg, was set for 59 and our frequency didn't ever quite get that low, it looks like it recovered and we were able to sustain these second two legs of the of the system. Go in and look at the log results. We can see that we initialize everything. All the motors are on. Cogen is on. Standby is on. We start to run the script. We pull open the device. Immediately, R1 starts to pick up on overcurrent. R2 picked up on under frequency, the 59.5. Then R2 trips on at 59.5. It sends a breaker to the feeder. It sends a signal to the feeder breaker, which then drops out. And we can see the second relay starts to pick up, but then as the frequency restores, then it resets and travels back. So the net result is, because of the response of the cogen, we were able to keep from recovering more than 1/3 of our load. Okay, same type of a simulation. If we want to look at what happens to the ATS if we lose the main bus, how does it transfer to the standby generator? So again, if we look at what that script looks like, we're going to run for 1 second, then we're going to open the fuse switch above the ATS, which is FS1, and then see what happens after that. FS1 is, where is FS1? Oh, right here. Okay, so it's in the main leg going down to the ATS. All right, so again, we want to see now on this one, we want to see the plots. Seeing what's happening on the cogen may be mildly interesting, but more important is on the standby generator and what that's doing to try to pick up on the load from this particular panel. So we're going to select ATS on standby, run the simulation. Okay, we can see on plot 1, which is a cogen, that there was a minor perturbation, but because we didn't lose much load, it didn't suffer much. But what we see on the plot 2, which was the bus on the standby generator, that as the ATS switched over, we're looking at the standby generator current, voltage, and frequency. As it picked up the load, its frequency dropped to 59.331 and then recovered. And you can see that the frequency and the voltage responded to that change in load. Now, one other example that's worthy, I think, of kind of pointing out, and let me just kind of jump into this. This was an example we did for a customer who was considering design of elevator controls, and the question was, what's the worst case scenario that can happen on my facility, and would my elevator controls survive? So the case that we kind of imagined was a medical facility where we have a backup or a duplicate utility supply, tie breakers that are necessarily independent. We have some substantial loads out here on the main bus and on the standby generator. If we were to lose power on the main, we'd have our elevator controls and then our mission critical systems sustained by a UPS. So as we go into simulation or into dynamic simulation, what we want to do is anticipate the potential for a fault on the main bus, the power switching over to the standby generator, and then whether or not all the elevators can be started at the same time and survive, or at least stay online. And as I do this, I notice the first thing that comes up, because we're in a power flow simulation, is that I've actually got some cables that I've missized for normal operations as I was putting together the example, because frankly I was more concerned about short circuit or arc flash, and this actually brings up the example that as the value of power flow. So let's kind of go in and I'm going to use auto design to kind of change these. Let's go back to stability. All right. Set up a script now that we've essentially had a full overlap between the starters for the motor. And what this looks like is full overlap. All right, essentially we run for 1 second, then we fault the bus, and then run for 7 seconds, and we set the motors to all be start at the same time, at the same value. Inside the motor modules, there are parameters that we can change during our editing process by just picking out where are they on the list and then assigning, in this case we're going to full on power, and effectively it's the same thing as turning the motor on, and we can do that in our script. So now as we pick out full start overlap and simulate it, what we expect to see is the bus default here, the ATS transfer over, which it did. We can see that all of our elevator motors stalled because we tried to start them at the same time. And here on plot 1, we're looking at the bus on bus 15, which is where the tie-in is for the elevator controls, and the current on bus 17, and that's essentially, where's bus 17? That's the total current that's being drawn, and you can see that as we try to start the motors, everything started and then hiccuped. So let's reset this, try a partially overlap and see if they survive. And again, we've just essentially set up in a partial overlap a 1 second. So we start the motor, run for 2 seconds, and start another motor. So we have a 2 second overlap. Let's see if they survive that. All right, here you can see that with the 2 second delay from the time, so we have a block of time that we run to let the generator get up to speed before we start, or let the ATS switch over and the generator get up to speed before we start turning the breakers on. But here we can see the result of each motor coming on the elevator, and then the 2 second delay, and then the next motor coming on. So with that much of a delay between them, if we isolate or make sure that there's at least a 2 second span between the starting of each elevator motor, then all three would survive being on the standby generator power supply, which I thought was kind of fun to examine. And it does look at this not so much just from the generator controls, but from the system response to and the ability to support loads coming on that basis. Last week, you'll recall we talked about starting one major load and how it impacted the rest of the system. Here we're able to include the response to a generator coming online, and then because it's not as stiff as the utility or the main bus, inspect whether or not it's going to be able to survive multiple motors starting at the same time. Again, these are examples that are available for your examination and to see how the system, the tools work. The first two that we've covered were installed in the samples. If you've got any questions, by all means, there are more detailed tutorials online, webinars online, that get into specifically how to model motors and then import from the torque, speed, performance curves, the specific parameters on any motor that you're using, and or how to use generic. All right, appreciate everyone attending. If you got any questions, by all means, contact techsupport@easypower.com. You're welcome to send me an email if you had a specific question about this webinar, jim@easypower.com. And we look forward to your attending more refresher seminars in the future. Have a good one.